Okay, so what you see here is one of the early systems that we have developed. Since our early development, the principles haven't changed. What have changed is the optimization of the optomechanics, the optics, the optical path. But this system basically is the one that represents the fundamental flow of how the system tracks the eye. So you have here a representation of the eye, which is basically a optomechanical setup with various lenses and the retina at the end that is connected to a motor that allows the eye to move in angular and lateral positions. And this system is separate and represented by the screen which shows the angle of the eye, as in this picture. This is the eye tracking which is connected to the computer in the loop, which is a real-time computer. This display demonstrates various parameters. What we need to operate is basically to minimize the error that you see here to zero. And these two signals are the signals that are the commands to the MEMS. Now the output, which is very important for the rendering, is the angle that you see here. On this part of the screen, what you see is the graphical pipeline representation with low resolution and high resolution embedded in the center, and that moves according to the position of the eye as we move the laser. In this early prototype, the reason we use it till now, we have also integrated the green laser, which is coaxial with the IR laser, and we were at the beginning assuming that it would be fine for the user to ignore the laser. However, what we found out, since the optical axis and the visual axis are not on the same axis, the person would see the image, the spots somewhere at the side, and would try to follow it, and eventually, since the eye cannot do a 360-degree turn, we would completely move the eye to the periphery of the human vision. Now, what you see here, since there is a see-through system and you can see the world, you can see the green laser entering the eye, reflected back through the optical system, and part of it is escaping and hitting this page. So if we move the eye right now in a non-tracked mode, as Faris will present it to you right now, you will see that the beam will not move here. That means that the eye is a very good reflector. It doesn't distort the angle of the beam. Now, what we need to do is basically to track the optical axis, so the angle of the beam needs to follow the eye. So if we close the control loop, as it is right now, if we move the eye, what you see, it is moving up, down, left, right, according to the command that we provide to the eye. Now, the more important thing here to understand is that it is completely closed-loop operation. It is sampling the eye position 20,000 times a second, significantly more than any camera. It's measuring the optical axis of the eye, so it's independent of the relative position and imperfection of the eye itself. It is not dependent on the shape of the external part of the eye, since we measure the internal part of the eye. And it is a modulated signal, therefore we are completely insensitive to the ambient illumination conditions. So what you see here is basically we follow the eye. Now a very important thing is, as with every system, when you put your glasses on, you need to find the eye, or you need to find the position. So we will demonstrate to you the algorithm that actually searches for the eye. So what you see here is the green beam, and it will now perform a search pattern. So you see a spiral. Now this is the demo mode. Now we will switch to the operational mode, which is basically a real-time operation. And as you can see, you cannot see. You cannot see, right? Any of that. But basically, the idea is that the operational mode, the time to initiate and to bring the system online in order to track the eye, it's around 40 milliseconds. So significantly less than any other system out there. So we have the benefit of very high sample rate, for which any motion is actually a very slow motion. We have completely indifference to the ambient illumination and to the shape of the eye. The system is oversampling the position of the eye, and therefore it enables us to create very high resolution position sensing, which is basically at the level of what the human would consider to be the resolution of the eye, which is 1 arcminute. And all these benefits are demonstrated here.
What's the cone of the search?
So the cone of the search right now covers the cone of the various positions. It's it is a combination of angular position plus minus 10 degrees and plus minus 1 millimeter in the vicinity of that area. The last, but not least, so it takes us 40 milliseconds to initiate the operation. Now, if we blink, as I'm blocking the beam right now, what you see is the moment I remove the card, it immediately regains the position. This regaining of the position is less than 3 milliseconds. Now, in general, the whole system needed to be operational at a latencies below 5 milliseconds, because we consider that to be the fundamental latency of human reaction. This system operates at less than 2.5, so half of what this tolerance budget that we allow for everything. So we leave some margin for other systems to also kick in. Basically, that's the eye tracking in a nutshell. Now, if we move to the other side, so now you're wearing our modern generation of eye tracker. This is basically 4 generations after that one that you saw before. And now this system, what you see is the tracker that also tracks the eye in a form factor that is common to the projection system. So this system allows us to do already wearable tests as you are sitting in a headset. And what you need to do is to follow the stimulus. Now, as I mentioned before, on the other screen of the real-time computer, here it's exactly the same. So this is the error that we need to minimize, and that is the output report of the position of the eye. And basically the idea is that we need to minimize the error and report the right angle. Here, if you look at the stimulus, which is represented so if you look at the stimulus, which is represented by this small circle with a cross in the center, and you will follow it, you will be recorded with all the positions of the eye at various points in time. This is the fundamental operation mode of the system, and because we are not dependent on the shape of the eye or the structure of the eye, basically as long as your eyes are human, you will be able to be tracked in such a system. Now, another very important thing, if you look at the point, fixate on it right now when it is stationary, and rotate your head sideways while still fixating on the point, you will see that the tracker does not lose the position, which is another very important stage of this system, because this is the only way that you can track the position of the eye that accurately. Otherwise, you will need to go into the systems that have extremely fast cameras or extremely wasteful in the illumination and power. But because we sample the system 20,000 times a second, it means that any motion does not create any blur in the system. So this is basically it. Thank you very much.
Amazing.
Please come again.
Very impressive.
זה ביבש, אבל כאילו תחשוב שהכל עובד ויש פה מישהו מהנדס פגש. Okay, so welcome. This is the control lab, one of the control labs of the company. Here we develop control algorithms and basically the control model of eye trackers, which are, as I mentioned before, based on laser reflection and tracking of the optical axis of the eye. Now, what you see here, Sonia, vuole po'. So what you see here is one of the early generations. The beauty of the fact that we have stayed with the same concept of tracking the optical axis is the fundamental benefit of such a technology. So what you see here basically is the eye tracker, which illuminates this part, which is a representation of the artificial eye. It has various optical surfaces that are similar to the human eye, and there is a retina that reflects the light back. Now, the eye is connected to motors that are actuated in various angles, and therefore we can see the position of the eye at any given point, because it's ground truth. We command it. So this you can see here on this screen with the head of a person and the constant readout of the angle of the eye. Now, the eye tracker itself is connected to this computer in the loop, which is a real-time computer, and its readout is demonstrated on this screen. As I mentioned before, the system operates in closed-loop operation mode. Therefore, we minimize the error to 0. So here we would like to see 0. The commands in order to that enable this operation are these two commands, which control the two dual axle MEMS, and the readout, which is this part, is the angles that go to the rendering pipeline that enable us to render the right angle for the position of the gates. And that is demonstrated here with the low resolution part and the high resolution part inlaid in the low resolution image that is projected and superimposed on reality. So this is more or less the main features of the system. Now the system basically what it does, it uses infrared laser to illuminate the eye, and the beam goes back and is locked to the minimum position on the sensor that is predefined as the optical axis. As you can see here, we have also a green laser. The green laser was actually intended at the beginning to be a pointer that would enable the user to see the image. However, we didn't realize at the time that the bright spot in the field of view, near the center of the field of view, would distract the user, and the eye would follow that spot. So in the later versions, we eliminated this laser pointer. However, this is...
Okay. So you're following the optical axis, not the visual axis.
Exactly. So we follow the optical axis, and we assume various parameters about where is the visual axis, because for each person the visual axis is something different. But for everybody the optical axis is the same.
So you're going to track the optical axis, but you're going to project the visual axis?
We will shift the image according to the visual axis. Okay. Now what you see here, since the laser, the green laser hits the retina and goes back, and this is a see-through system, part of the green laser also escapes to the screen, and you can see the position of the beam on the screen. Now, before we track, if we actuate the eye, what you will see is that it will assume various angles. However, the beam does not move on the screen. And that means that the eye is a very good retroreflector. It really reflects the beam exactly to the angle in which it came from. However, when we want to track the optical axis, it should move according to the optical axis of the system. So what we will do now is to close the control, as you see now. And now if we move the system, you can see it moves according to our command. You can see here the error still stays 0, but the readout of the angle changes according to the position of the motors. Another thing that you can also observe is the shift of the image according to the angle of the eye. So this is a principle of the fundamental operation. Now, obviously, we will need to operate it in such a way that when the moment you put the glasses on, you need to find the eye. So, in order to do that, we have developed an algorithm that searches parameters of angles and lateral positions of the eye, in order to detect the position and close loop, to do initial close loop. So what we'll do now, we'll open the loop, as you can see now. Now we'll shift the eye to some angle, and then we'll try to close the loop. We press the button. Now we will demonstrate it to you in demo mode, which means that we'll deliberately slow down the mirror. So you can see it does this spiral shape. Now, after you see that it has closed the loop and it follows the eye, we will move the eye again. But now we will do it in real-time operation. So please look, this is the initial position, and now we try to close the loop. It has been closed. So that effect took only 40 milliseconds. So just let's talk a little bit about numbers and the performance of this system. In order for us to acquire accurate position of the eye, it takes just 40 milliseconds. Now,
so every time the tracker will lose tracking of the eye,
not exactly.
it will take us 40
So every time you put on your glasses, it will take 40 milliseconds to get an image. I'm not sure that actually your eyes can acquire the image so fast when after they have been exposed to some motion, which is significant. So this is a very fast acquiring method that we can do. How do we achieve it? We do very high sample rate. So we sample the eye position 20,000 times a second, and we have demodulated the signal, so no ambience of ambient conditions actually can affect the position of the eye in any given moment.
תחשוב ככה שאתה עובר אחר כך לעבוד פרוז'קשן. אוקיי, ואם אתה מדבר על הספירלה הזאת, אני לא יודע אם נצליחו בארץ. מישהו יכול להבין שעזור every time you run away you do the spiral.
תכף, חכה, למה אתה לא מסוגל? So this is for the initiation of the system. And just to finish the numbers part, when we want to sample it so fast, we are tracking within a relatively large angle. However, because of the sample rate and because of the oversampling and the modulation, we also get a very high dynamic range, meaning that the resolution of the system is in the order of magnitude of 1 arc minute, basically on the natural resolution of the eye. Last but not least, many of the eye trackers nowadays dependent on the shape of your eye from outside, or how much your eyelids are closed. This is an on-axis system. So as long as your eye is constructed more or less like a human eye, not like a sheep's eye or octopus eye, you will get very accurate position of the system on the optical axis. This is fundamental to this system. Now, on the side of actually getting the operation when you, for example, blink, what we can do is let's interrupt the beam like an eyelid. We'll do that. As you can see here, the system gets an error, and then it is going back. And also the pipeline, graphical pipeline, you disturb it, and then you get back. So as if you are already locked initially in the position of the eye, to regain lock after there is some kind of disturbance is very, very fast. It's below 5 milliseconds. So the reason why we have developed this unique eye tracker is in order for us to get very, very accurate operation in a method that we can do everything below 5 millisecond latency. This specific approach with these mirrors takes only 2.5 milliseconds, so we still have half of the time for various other high latency things to do. So this is the eye tracker and how it operates. Now we can move to the other side, and I will show it on you, the system, and how it tracks your eye and what it does.
Okay.
So now, when you wear our eye tracker already on your head, here you can see the same screen. So when we track this readout is 0. this is the readout for the graphical pipeline, and these two upper charts are the commands to the mirrors. Here you can see the stimulus, and what we can do is
You have two mirrors here.
so the system has to compensate for at least 4 degrees of freedom. The eye can move angularly as well as laterally. So in order for you to compensate at least for 4 degrees of freedom, you need 4 degrees of freedom in your system. You cannot do it with less. There is a fundamental determinant issue of how you define your space of degrees of freedom.
So here we have the IR laser going to my eye.
So here the same principle, only this system is based on the architecture that we already use for the projection. So it's a common architecture for projection and eye tracking.
Is it safe?
Of course. So in any system, what we do is we first of all measure the optical power, and we make sure, check and double check that it is by design not exceeding the limit of permissible limit of exposure. And the other thing that we also do is we modulate the signal. So even if everything is not operational right, there is no reason why we will get more than the permissible exposure level. So it's completely safe. Please, we aligned it for so many seconds on you. So now what you can see is basically you can follow the stimulus. The stimulus jumps from one point to another, and you need to follow it in such a way that that you get very accurate fixation on the stimulus. So on the screen, the rest of you people, you can see that the error almost doesn't change from the 0. It jumps sometimes because this is the saccade that the user is making. However, the readout reports the right angles for the stimulus position. Now, another thing that this system can do uniquely, and this is quite a proprietary ability of such a system, if you fixate in one spot and you try to rotate your head while following that spot, what you'll see is that the system is doing a smooth pursuit. Basically, it follows your eye even in motion. Usually, eye trackers that are camera-based either have these frames smeared or have some issues with various artifacts that do not report the position very accurately. This system is independent of all these aspects of motion because we sample, as I mentioned, very, very fast. Therefore, you get a very, very accurate tracking, even in the motion of the eye mode. So this basically is the eye tracker to our best knowledge is the most accurate and the fastest, and a very, very important thing that makes it an ideal system for AR. It uses a very small amount of power. It has very low power lasers. It has almost zero power consuming MEMS, and it has a very, very efficient algorithm to operate. Therefore, unlike camera-based systems that are at least 2 watt or more, this system has a very low power, and therefore it enables us to make it operational 24/7.
But you also have cameras here, I see.
So right, the reason we have cameras is because it's a hybrid system, meaning that whenever the eye tracking, which is laser-based eye tracking, goes out of the range of the ±10 degrees that we specify as the operational mode of this laser-based eye tracker, we go into the part which is basically the area of camera-based system. So this is used only when you move your eye in ranges that are beyond the one that the eye tracker is intended for. Just to make it, put it into proportion, during the day, saccades that are larger than the 10-degree cone or 20-degree cone are less than 0.5% in its relative amount.
So the cameras are usually closed? How does it work? How does it
Exactly,
know when
exactly,
I go outside?
exactly. So the cameras are used only in unique cases, whether it is something that we need to do like a sanity check, or when we understand that the system has moved beyond the plus minus 10 degree range.
So
The rest of the time,
how do you
the
know these situations?
so we have the laser-based eye tracker, and in the beginning we operate everything obviously, but then the hybrid operation mode means that we can choose to use either the cameras or the laser-based all together, and we do it in a smart state machine management way that we can transition from one mode to the other almost painlessly.
So what would be the real benefit of energy consumption if we take also these cameras into account?
So the cameras work less than 0.5% of the time. So the benefit is still there. This system is 1,000 times more efficient on the laser side, and then there is another addition of 0.5%. So it's still less than 1/20th of the power consumption of a normal operating eye tracker. Basically, that's it. Thank you for visiting EyeWay. Please
Thank
come
you.
again.